Thank you, Sabrina, for the presentation. I'm really happy to be here today to present this work. This is a joint work with University of Porto and University of Texas Austin, and we are running right now a project on this topic. And I've been collaborating with the University of Porto since many years, especially with my friend Jose Correa. Before starting, I want to thank Professor Fantuzzi, Professor Iacoviello for allowing me to present this talk here. Just a few words about my university. Actually, I'm affiliated with the University of Bologna, but I work at Ravenna campus. Ravenna is a city nearby, 50 kilometers from here. Why Ravenna? Ravenna is the central hub of Italy of oil and gas. And in the future, we hope of renewable energy systems. This is just a screenshot that shows you where the platforms are located, starting Ravenna in the north, Rimini, San Marino area here, until, Ancona area and down below. In Ravenna, we have a master called Offshore Engineering for Energy Transition, which we give lectures about offshore structural dynamics, fatigue, materials, processes, etc., etc. Why we have this master? Because my department is quite large. We are the Department of Civil, Chemical, Environmental, and Materials Engineers. So we basically gather all our knowledge, which comprehend basically the offshore sector. So let's jump into the presentation. Let me just switch to time. So motivation of this talk is the following. Basically, this is something that Europe is asking us to decarbonizing the oil and gas sector. And the procedure that we would like to apply is so-called global local fatigue analysis. And I'll try to give you some insights about this. Another motivation why we're considering fatigue, maybe you know already, but fatigue is one of the most reasons of accidents, both in oil and gas installations and wind turbines, which is at the moment the commercial solution for renewable energies. Of course, there are other solutions, solar panels, tidal waves, and others, but this is commercial and worldwide accepted from China to the United States. So if you're not familiar with the offshore environment, basically we have to start with, structural engineers to change environmental loads into actual forces. And we do that starting with mid-ocean data, which are given by oceanographers. And basically we use wave modeling, which is a well-known Morrison equation, and wind modeling, which can be, taken from high-rise buildings and bridges. For structural integrity, I don't have to explain to you because you're expert already, but what we're gonna apply is, precipitation factor concept, union multi-action fatigue approaches. Then we'll show you some later, in order to get a fatigue damage assessment of the structure. This gives us an idea, rough idea of how many years we can keep the structure in place without demolishing it. So migration analysis, I will just give you a brief, just a few slides, how to get those data, or to take data from literature. We are lucky because we have some real data that we are able to extract. Two ports in Portugal, the Açores, which is the port of Porto, and Sines, close to Lisbon, and Tillamook, United States. Then we extracted some data from the so-called scatter diagram, which is, sort of sketch that probabilistically give you information about wave loads. So migration data are in this form, a little bit complex. We need to synthesize those data to extract information that are needed for us. Mostly we need significant wave height, which is the top here, which is a key parameter in offshore, and the period associated with that significant wave height, as well as wave direction, because clearly waves, they come from different directions, from 0 to 360 degrees. Migration data are available in the literature, and we extracted some data from the Northern Atlantic Ocean, and are in this format, tabular format. Basically, they are obtained through buoys that are located within, ocean or sea locations in the world. And from those tables, we are able to extract wave height, so significant wave height, and wave period. With those data, we basically get a statistic description of the load, which is not deterministic, or at least from the statistical distribution we can extract deterministic view of the load to run deterministic analysis, like time history analysis, or stochastic analysis. When we talk about decarbonisation, we must introduce the topic of decommissioning, because this is quite, I guess, find these discussions in many posts on LinkedIn and in papers. And decommissioning follows, these 5 rules, which is prevention, reuse, recycling, and disposal. And of course, what we want to do is reuse. So we work on prevention as much as we can when we cannot do any more with this sort of reuse. And we try to reuse an oil and gas platform for other purposes, in this case, for green energy. And unfortunately, what we don't want to do is disposal of the platform. But decommissioning is not only engineering, not only mathematics. That is several different things, especially laws and regulations. So decommissioning in Italy or Europe is different from decommissioning in the United States, different from decommissioning in North Europe, etc., etc. So we always have to follow laws, and sometimes it is not possible to reuse and therefore dispose, because you have to bring back the status of the environment as it was before the oil and gas condition. But I'm not talking about that in this presentation. Just assume that you can reuse the platform as it is and continue to use the site. So from the mechanical point of view, it is a quite simple procedure. First, you cut the well, and then you remove the deck, and then you just, remove foundation and remove the jacket if you want to decommission the platform. So this is quite easy procedure to do. If you want to reuse, you have to stop at number 2. So you just close the well, remove the deck, and do something else. As a start for global analysis, we perform some reduced order modeling. So we take a dummy platform and just model this platform with reduced number of degrees of freedom. This allows us to have quite fast and reliable model. I will show you some results to perform retrofitting activities. Clearly, with this model, we lose information on details, but it's not the purpose of the global modeling. The global modeling just requires you to have indication about what is the status of the platform at that stage. So as you see, we compare, this is MATLAB discrete reduced order model with sub 2000, and in terms of dynamics, the model was quite good. This is time domain solution, and this is a frequency solution. As I said, it's quite straightforward to do retrofitting in the sense that we assume we are removing the deck and we install the turbine, which can be, horizontal or vertical axis in this case. I'm not going to discuss details of these two turbines. If you want, we can discuss later. But basically, you can just run again, and results are quite nice. Unfortunately, when you go to stochastic analysis, there's a problem at the top, because of course the platform was not designed to bring, long beam on top of that. So you should go to retrofit, and you can strengthen the structure in different ways, or just install a smaller turbine. And these are some results that we carried out. I just, focus your attention on this line, which is a smaller turbine, because you will see something similar in the end. Just to see what is the difference between installing a 5 megawatt, in this case, not 2 megawatt turbine, for the peak life of the structure. Okay, regarding fatigue, what we have carried out, actually, this was PhD work of our student, Paolo. We studied several specimens, especially we are interested in welded parts, because they are the most hotspot areas in a platform. And we performed uniaxial and fatigue tests. These are some of the results that we obtained for 30 and 60 millimeters plate. As you can see, there is some scattering in the data. This is also summarized here. So especially nice cycle fatigue. And then we noticed there was a reducing fatigue resistance due to the heat affected zone of the weld, and also the increase of thickness negatively impacted on the fatigue resistance. As you see, there's a difference between these two curves. This is 30 millimeters, and this is 60 millimeters. The slope increase. Okay. Just for the record, I reported here some optical images on the fracture surface. So we observed some secondary crack on the specimens and some striations during the process. And these are just two pictures, one in high and one in middle fatigue. This is about 2 million cycles. It's about 150,000 cycles. Okay. Just to go to the probabilistic fatigue strengths that we computed, basically we used two classical methods, linear regression or orthogonal linear regression. As an input, we have our experimental fatigue data, and the aim is to obtain the curve of estimating fatigue life in the end. So specimens are exactly the same, uniaxial and rotating. This is just a closer look at strain gauges for evaluating hotspot stress. So I should just about that. And this is the machine that we use for fatigue data in case of welded joints. Same welded joints that I showed you before, 30 millimeters and 60 millimeters. Okay, some results. The dots, of course, of experimental data, and the lines that have been obtained with several approaches, considering 5% of failure. So there's already taking into account safety factor. There is some inconsistency with some models, but most of them are in line with data that have been considered. This is for the hotspot calculation and the nominal stress for the stress. Of course, I have a lot of results that I decided to cut because maybe it becomes a little bit not interesting, but clearly in a platform we have joints that are in air and joints that are in water and joints that are in the so-called splash zone. So the most harsh part is the splash zone, and so it's important to perform tests on the corroded specimen, which leads into some decrease in the fatigue life, clearly. So basically, you can see these curves with corrosion effect, it just go a little bit lower. Okay, this is why I said not to show, but there's also close to these trends. All right. So this slide basically shows the overall procedure. So we start with some data, then we perform global analysis, the one I showed you before. And then we have an inelastic analysis to identify critical details. So first we do global, then we go for a more detailed global steel analysis to identify critical joints. Then we go for submodeling, and in the submodeling we have to extract the intensity factor, and other fracture mechanics parameters that we all know. And then we have fatigue damage estimation. So this is the aim, right? We take a platform, which is oil and gas. We just remove well and we remove deck. We have to introduce something a little bit complicated, which is called transition piece, and install with the pipe. And why I'm saying that transition piece is, actually still an open topic because we don't know how to do it. Many companies do it in different ways. So we studied this design, which is main piles on a plate. Reinforcement, they go to the legs of the platform. But as you can see, there are some operations with plates and hotspot stresses in the joint. Yes. You will find in the literature many different designs of this transition piece. So actually, during the conversion, we have the classical hotspot in the joint of the platform, which they are more critical due to the heavy loads with the tower, plus the joint in the transition piece. So we have extra joints to verify, and the original joints that are at reduced life due to maybe 20-25 years of operation, they have to be strengthened. So these are some pictures of the submodeling. So just studying transition piece using abacus, using as boundary conditions the legs and the tower up top. And these are some of the stress and history curves that are used for fatigue analysis. So for the critical weld joints, we have more or less sinusoidal approach, and for the transition piece, this is more like random load. This is why transition piece is a little bit more difficult to verify. And by using our global stress analysis, which is quite standard procedure, we are able to compute a fatigue life for the oil and gas, let's say, time frame, and a fatigue life for the offshore wind turbine phase. And the output of the model is something like this, in which you have some, still after 30 years, you have still some fatigue life available. Then you perform some retrofitting, and then you apply wind turbine. So I said before, right? Remember the 2 megawatt turbine. So this is the difference for the case we are studying, which is a dummy model. Difference between installing a 5 megawatt turbine or a 1.5 megawatt turbine. So to look at the difference in the residual. So of course, we open a discussion now. We install a larger turbine, so we make more energy, theoretically, but the platform, lasts for less time, or we just, when we just install a smaller turbine, we make less energy, but we can make it for more time. And this kind of simulation is not enough, really, because here, if you want to see the overall picture, you should include economical, variables for installation and maintenance costs in this analysis. We cannot only look at the single life on the platform. Okay. Just show a few slides to conclude, and what we are just looking at. We are working with this company, and we use software Axelos, which is a software developed by MIT in the States. Basically, this is a reduced order model finite element software, which is able to implement data-driven analysis. So by taking data, you can have estimation using machine learning techniques on the platform. So the aim is to basically compare our approach with this commercial software and see what are the advantages and disadvantages. Clearly, and a clear advantage of Axelos is that it works in a reduced order model approach, which means basically it runs in the cloud extremely fast compared to classical finite element analysis. So this allows you to get results in a very fast way, just using a browser. So that the software runs in the browser and the software runs in the cloud. These are just some pictures that are taken from the software. This is not a classical finite element software. It's a component-based software in which the elements are within each component. So each component is with several elements. This requires some extra effort in making the original model, but then you have basically everything you have from a standard finite element software, which is displacement, forces, and I think this is the utilization function. This is based on fatigue analysis done within the software. Yes, this is the analysis. Okay, so procedure is standard as any other finite element software in offshore, just done much faster. Okay, so yeah, this is just some other results on critical joints. See, the software is able to identify it, but also, of course, for the analyst. Okay, I think I can just finish my talk. Basically, we try to demonstrate that global local fatigue approach is a viable alternative for decarbonisation and strategy for the reuse of platforms, if possible, because it's not always possible everywhere. Just to stimulate the discussion, I want to leave you with this phrase. This is a professor in the United States. So if you really think that the environment is less important than the economy, try holding your breath while you count your money. I also want to thank Reworks from the Fene Flaminia from Ravenna and the Association of Offshore Contractors in Ravenna.